In this video, we will look at how we can search for an element in an array. We will look at two different kinds of searches that can be performed on arrays. First is linear search. In linear search, we search for an element by traversing the array sequentially from the beginning of the array to the end. At each index, we check if the element at that index equals the search key. Second is binary search. In binary search, we search for an element by repeatedly dividing a sorted array into binary search intervals. At each binary interval, we check if the element at the middle index equals the search key. For each of these two search algorithms, we will review the key concepts. We will look at the steps of the search algorithm. We will look at an animation of how the algorithm works. We will look at the sample code or pseudocode. Then, we program the search algorithm in Java and test our program. And we will see the efficiency of the program. Let's begin by looking at linear search. In linear search, we traverse the array element by element sequentially from the beginning of the array until the end, or until the search key is found. At each index, we check if the element value equals the search key. We usually stop the traversal if we find the search key, unless there is a requirement to find duplicates, in which case we have to traverse the array until the end. To perform linear search, the array need not be sorted. This is unlike binary search, where the array has to be sorted before we can perform the binary search. Linear search is less efficient when compared to binary search for large data sets. Let's now look at the steps of the linear search algorithm. First, we traverse the array starting from index 0. At each index, we compare the value of the element at that index with the search key. If value of element is equal to search key, then we stop the traversal and return the index where key is found. This is assuming that we are not required to find duplicates. If we are required to find duplicate elements, then we continue to traverse until the end of the array. If we traverse the complete array and the search key is not found in the array, then we return -1. Let's look at a visual of the linear search algorithm. We have an array of length n. The index of first element is 0, and the index of the last element is n-1. Let's refer to this array as my array, and it is of length n. Let's say the search key is 7. That is, we want to check if the array contains an element with value 7. So we traverse the array starting from index 0 and check if the element value at each index equals 7. So, element at index 0 is not 7. Element at index 1 is not 7. Element at index 2 is not 7. Element at index 3 is 7. So we stop the traversal and return the index at which 7 is found. That is index 3. Let's now look at sample code. We define a method named linear search that takes the search array and the search key k as parameters and returns the index at which the key is found. -1 will be returned if the key is not found in the array. We then traverse the array and at each index check if the element value equals the search key. So we have a for loop with I starting from 0, I less than my array dot length, and I ++. And within the for loop, we check if the element value at I equals the search key. If it is equal to search key, then we return the index. After the for loop, we return -1. So if the key is not found, then we return -1. Now, let's look at the efficiency of linear search. Since we traverse the array element by element, the time complexity of linear search is O of n, where n is the length of our array. In linear search, we define one additional attribute I as part of the for loop. So the space complexity of linear search is O of 1. Let's now code the program to search for an element in an array using linear search. So we have our class and the main method that we will later use to run and test our code. Let's create a new method named linear search that takes the search array, say my array, and the search key int k as parameters. This method returns the index of the array where the search key is found. If the search key is not found in the array, then this method should return -1. Next, we will traverse the array. So we have the for loop, int I is equal to 0, I is less than my array dot length, and I plus plus. Within the for loop, we will check if element at index I equals the search key. So we will have an if condition, and we will check if element at index I is equals to the search key k. If element at index I equals the search key, then we return the index. And outside the for loop, we will return -1. So if the search key is not found in the array, then we would return -1. Now that we have our method, let's take some test data and run it through the main method. Let's go to the main method and create our test array. Int array, my array, is equal to new int array. And let's add some sample data. So here we created an array of size 10 with values ranging from 2 to 75. You can see here that the values are not sorted. Remember, to perform a linear search, the array elements need not be sorted. Now let's call our linear search method to search for a key in this array using linear search. So int index is equal to linear search, and we will pass my array. And let's say we want to find the key 7. Let's now print the index so that we can run and test our program. System.out.println, and we will print index. So our method is ready and we have our main method to test the program. Let's go ahead and run this program. We can see that the index returned by the method is 4, which is expected. Now, let's search for a key that does not exist in the array and see if the method returns -1. So, let's change the key to 32, which does not exist in the array, and run our program again. We can see that the index returned by the method is -1, which is expected. Let's now look at binary search. In binary search, we start by checking if the middle element of the array equals the search key. If the middle element equals the search key, then we stop the search and return the middle index. If the middle element is not equal to the search key, then we ignore the half in which the element could not exist. We will consider only the half in which the search key could exist. In this half, we again compare the middle element with the search key. We continue this process of dividing the array into halves and comparing the middle index with search key until the search key is found. If the array cannot be divided further, it means the array does not contain the search key. Usually the search is stopped once the search key is found. One of the prerequirements to perform a binary search is that the array must be sorted. Compared to linear search, binary search is more efficient than linear search for large data sets. Let's now look at some of the terminology we will use for binary search. Search key. This is the value that needs to be searched in the array. Search interval. This is the list of adjacent indices, or the half that is considered for a search step. Low index. This is the index where the search interval starts. High index. This is the index where the search interval ends. Middle index. This is the middle index of the search interval. Let's now look at the steps of binary search algorithm. First, we consider the whole array for the search interval. That is, low index is index 0 and high index is index n minus 1. We then check if the search key is equal to the middle element. If the search key is equal to the middle element, we terminate the search and return the index. Else, if key is smaller than the middle element, then the key cannot exist on the right side of the middle element, since the array is sorted. So we eliminate the right side and continue our search on the left side. So the left half becomes the new search interval. The left index remains the same. The right index is now one index less than the middle index. On the other hand, if key is larger than the middle element, then the key cannot exist on the left side of the middle element. So we eliminate the left side and continue our search on the right side. So the right half becomes the new search interval. The left index is now one index more than the middle index. The right index remains the same. We continue this process of dividing the array into halves and comparing the middle index with search key until the search key is found. Let's quickly check how we calculate the middle index. The middle index is calculated by taking the sum of low index and high index and dividing by 2. But this could have an issue of int overflow. In the case of very large arrays, the sum of low index and high index could become greater than the max value of int. This would lead to incorrect result or an error when we perform the binary search. To overcome this issue, we slightly change this equation. We first take the difference between high index and low index, divide by 2, and then add the result to the low index. This prevents the int overflow, but the end result would be the same. Let's now look at a visual to understand the binary search steps better. Let's take a sample array of size 11. The index of first element is 0, and the index of last element is n minus 1, which is 10 in this example. Let's refer to this array as my array, and it is of length n. The first step we do in binary search is to take the complete array as our search interval. So the low index is 0. The high index is n minus 1, which is 10 in this example. The middle index is calculated using the equation middle index is equal to low index plus high index minus low index divided by 2. That is 0 plus 10 minus 0 divided by 2, which equals 5. Let's look at this on our array. So low index is 0. High index is n minus 1. That equals 10. The search interval is the complete array, that is, from index 0 to index 10. The middle index is index 5, which has an element value of 30. Now, when we compare the middle element with the search key, there could be 3 outcomes. Let's consider the first outcome, which is the search key equals the middle element. In this case, we stop the search and return the middle index. Going back to the array, in this example, if search key is 30, then we stop the search and return the middle index 5. Let's now consider the second outcome, which is the search key is less than the middle element. In this case, the left side of the middle index becomes our new search interval. We will not change the low index, but the high index now becomes middle index minus 1. We will calculate the new middle index using the same equation. Going back to the array, low index remains index 0. high index is now one index left of the middle index, which is index 4. Our new search range is from index 0 to index 4, and the middle index based on our calculation will be 2. Let's now consider the third outcome, which is the search key is larger than the middle element. In this case, the right side of the middle index becomes our new search interval. The low index now becomes middle index plus 1. We will not change the high index. We will calculate the new middle index using the same equation. Going back to the array. High index remains index 10. Low index is now one index right of the middle index, which is index 6. Our search range is now from index 6 to index 10, and the middle index based on our calculation will be 8. Now that we have seen the three different outcomes of a binary search step, let's look at a couple of examples. In the first example, let's search for the key 20 in our array. For first search step, we will consider the complete array for our search interval. Low index is 0. High index is n minus 1, which is 10. Middle index is 0 plus 10 minus 0 divided by 2, which equals 5. So in the array, the low index is 0. High index is 10. The search span is from index 0 to index 10, and the middle index is 5. The search key 20 is less than the middle element 30. So we will ignore the right side of the middle index and search the left side of the middle index. Let's determine our indices for next search step. So for the second search, the low index remains 0. High index is now middle index minus 1, that is index 4. And the new middle index is 0 plus 4 minus 0 divided by 2, which equals 2. Going back to the array. Low index remains at index 0. High index is now 4. New search interval is from index 0 to index 4. And the new middle index is 2. Element at index 2 is 15. Our search key 20 is greater than 15. So we will ignore the left side of the middle index. We will consider the right side of the middle index for the next search step. Let's determine the new indices for the next search step. So for the third search step, low index will now be middle index plus 1, that is 2 plus 1, which equals 3. High index remains same, that is index 4, and the middle index is 3 plus 4 minus 3 divided by 2, which equals 3. Please note that in Java, 1 divided by 2 is 0, since the decimal portion is truncated. Now let's go back to the array and mark our new indices. So low index is now index 3. High index remains the same, which is index 4. The new middle index is index 3. Element at index 3 is 20, which is equal to our search key. So we return index 3. This concludes the first example, in which we successfully found the search key that is on the left side of the array. Let's now look up another example. This time, let's search for a key that is on the right side of the array. Let's say 40. First, we will consider the complete array for our search interval. So, low index is 0, high index is n minus 1, which is 10. Middle index is 0. Plus 10 minus 0 divided by 2, which equals 5. So in the array, the low index is 0. High index is 10. The search interval is from index 0 to index 10, and the middle index is 5. The search key 40 is greater than the middle element 30. So we will ignore the left side of the middle index and continue our search the right side of the middle index. Let's determine our indices for the right side. So for the second search, the low index is now middle index plus 1, that is 5 plus 1, which equals 6. High index remains the same, that is index 10, and the new middle index is low index plus high index minus low index divided by 2. That is 6 plus 10 minus 6 divided by 2, which equals 8. Let's map these on the array. So, low index is now index 6. High index remains at index 10. New search interval is from index 6 to index 10, and the new middle index is 8. Element at index 8 is 45. Our search key 40 is less than 45. So, we will ignore the right side of the middle index, and we will consider the left side of the middle index for the next search step. Let's determine the new indices for the next search. So for the third step, low index will remain the same, that is index 6. High index will now be middle index minus 1, that is index 7, and the new middle index is low index plus high index minus low index divided by 2, that is 6 plus 7 minus 6 divided by 2, which equals 6. Again, remember that in Java, the decimal portion is truncated from the result when two integers are divided. So, 1 divided by 2 is 0, and 6 plus 0 equals index 6. Now, let's go back to the array and mark our new indices. So, low indexes remain same at index 6, high index is now index 7. The new search interval is from index 6 to index 7. The new middle index is index 6. Element at index 6 is 35. The search key 40 is greater than 35. So we will ignore left side and continue our search on the right side of the middle index. Let's determine the new indices for the next search. So for the fourth step, low index will now be middle index plus 1. That is index 7. High index remains the same, that is index 7. And the new middle index is low index plus high index minus low index divided by 2, that is 7 plus 7 minus 7 divided by 2, which equals 7. So now all the three indices, the low index, the high index and middle index, points to the same index, that is index 7. Now let's go back to the array and mark our new indices. So low index is now index 7, high index remains at index 7, and middle index is also now index 7. The element at index 7 is 40, which equals the search key. So our search is successful and we return index 7. This concludes the second example in which we successfully found the search key that is on the right side of the array. You can extend this example with a key that does not exist in the array, say 41 or 42. Once the low index and high index points to the same index, the search interval cannot be split further. And if the search key is not equal to the element at this index, that means the array does not contain the search key. Let's now look at the code for binary search. We define the method for the binary search, and we pass the search array and the search key k as parameters to the method. This method returns an int, which can either be an index of array if the search key is found, or -1 if the array does not contain the search key. Let's now define the variables for our indices. So we have low index initialized to index 0, high index initialized to my array dot length -1. So our search interval to begin with is the complete array from index 0 to the last index. And we define variable for the middle index. This will be a recurring search. So we will have a while loop and we search iteratively while the low index is less than or equal to high index. First, we will calculate the mid index using the formula mid index is equal to low index plus high index minus low index divided by 2. We then compare the search key to the element at this middle index, and that will result in 3 outcomes. First case, search key is equal to the element at mid index. In this case, key is found, so we return the middle index. Next case, search key is less than middle index. So we consider left side. We set high index to mid index -1. Third case, search key is greater than middle index. So we consider the right side. We set low index to mid index +1. After the while loop, we return -1. If this line gets executed, it means that the search key is not found in the array. Let's now look at the efficiency of binary search. In binary search, for every iteration, the size of the array becomes half. So, in the worst case, the number of steps we have to execute is log n, where n is the size of the array. So, the time complexity of binary search is O of log n. In the binary search code, we define 3 attributes for the indices. So the space complexity of binary search is O of 1. Let's now write the code for binary search and test our code. So we have our class and the main method that we will later use to run and test our code. Let's create a new method named binary search. That takes the search array, let's say my array, and the search key int k as parameters. This method returns the index of the array where the search key is found. If the search key is not found in the array, then this method should return -1. Within the method, we will first define the variables for our indices. Int low index is equal to 0. Int high index is equal to my array.length -1. So our search interval to begin with spans from beginning of the array to the end of the array. Let's also define the variable for mid index. Int mid index. In binary search, we iteratively divide the array and search. So we will have a while loop. Low index is less than or equal to high index. So we will iterate until low index becomes greater than high index. Within the while loop, we will first calculate the mid index. Mid index is equal to low index plus high index minus low index divided by 2. Now we have to compare the key to the element at this mid index. Let's handle the 3 cases that this comparison will result in. Case 1 k is equal to mid element. So we will have an if condition and k is equal to my array and index is mid index. Since k is equal to the mid element, that is, the key is found at the mid index, we return the mid index and stop our search. Case 2k is less than mid element. Tells if k is less than my array at mid index. Since k is less than the mid element, we ignore the right side of the array and continue our search with left side of the array. So the high index becomes one index less from the mid index. We do not change low index. So high index is equal to mid index -1. Case 3k is greater than mid element. If k is greater than my array at mid index. Since k is greater than the mid element, we ignore the left side of the array and continue our search with right side of the array. So the low index becomes one index more from the mid index. We do not change high index. So low index is equal to mid index plus 1. Then, after the while loop, we return -1. If this line gets executed, it means that the key was not found in the array. Now that the method is complete, let's create some test data and run the program. Let's go to the main method and create a test array. Int array test array is equal to new int array, and let's add some test data. So we have created an array of size 20 with values ranging from 5 to 100. Since binary search requires the array to be sorted, the test data is sorted with values from 5 to 100. Let's define a variable for the key so that we can change the value to search while testing. Int key is equal to, let's say, 25. Then we will call the binary search method. Int found index is equal to binary search, and we will pass test array and key. Let's print out the index so that we can check if the value is correct after running the program. Let's run the program with key 25. As we can see in the console, 25 is found at index 4, which is correct. Let's test with a few more values. Let's change key to 40, run again. 40 is found at index 7, which is correct. Change key to 75, and it is found at index 14. Let's also test the extremes, that is the first and last elements. Change key to 100, and it is found at index 19. Change key to 5, and it found at index 0. Now let's test a value that does not exist in the array. Change key to 6, and response is correctly -1. This completes the binary search program. This also concludes this session on linear search and binary search. But before we end this video, let's quickly summarize the differences between linear search and binary search. In linear search, we traverse the array element by element sequentially until the key is found. In binary search, we iteratively reduce the sorted array by half and search for the key in the middle element. Array need not be sorted to perform a linear search. Array must be sorted to perform a binary search. The time complexity of linear search is O of n. The time complexity of binary search is O of log n. Linear search is less efficient for large arrays. Binary search is more efficient for large arrays. Linear search is preferred when the array is very small or when the array is unsorted, and when the cost of sorting the data would be too high. Binary search is preferred when the array is already sorted or when the size of the array is very large. Thank you for watching. Please visit our website interviewgrid.com for more topics and frequently asked interview questions and answers on these topics. If you liked this video, please subscribe to this channel for more of similar videos.